Now, when we have an equation that looks something like this, 2x equals 7, we'd like to be able to solve for x just like we've solved for many other kinds of equations that have x in them. The only thing is it's a little bit trickier to solve for this x than some of the other types of equations that we've tried to solve. And so it turns out that in order to get that x all by itself, we need to take advantage of something called logarithms. And why? Why do logarithms help us? Well, if we take a look at something that we know, something like a power, like a square, and we say x squared equals 25, we know that we can get x all by itself by using the inverse of the square, which is known as the square root. And when we take the square root of both sides of the equation, we're able to get x all by itself. And we'd like to be able to do the same thing with that x up above. So in this case, we get plus or minus 5 for x using the inverse of the square. And so it'd be really nice if we had an inverse of this 2 to the power of x so that we could get that x all by itself. Turns out we do. It's called a logarithm. So what happens is this, is if we take a log base 2 of 2 to the power of x, it turns out what we get is simply x. Sort of like when we take the square root of x squared, we get x. And by the way, just I'll mention it, is that if we had square root of x and we squared that, we also get x. So when we have inverses if we have inverse functions, two functions that are inverses of one another, and we join them together, we make a composite function, we do a composition of functions of the two, we get x. This is something that we looked at when we looked at inverse functions and we tried to verify that they were inverses. So the next natural question for you should be, well, how does this work? And by the way, maybe I could make this a little clearer by, let me put some parentheses in here. We're saying that the log is a function, log base 2, and the argument of that function is 2 to the power of x. We're going to call whatever goes into parentheses, we're going to call that the argument. So the log is acting on this guy. When I have the log base 2 of 2 to the power of x, I simply get x. It's almost like these 2's cancel with each other. Let's take a look at another example. Let's see what you think of this. If I had something like log base 3 of 3 to the power of 5y, I simply get 5y. Hopefully you're catching on. If I have something like log base 7 of 7 to the power of 2m minus 3, that is the same as 2m minus 3, because this 7 and this 7 cancel. The log base 7 of 7 to some power just gives me that power. And it's because of the inverse nature of logs and exponentials. I apply a log to an exponential, I simply get the power. That's like magic. Now let's take a look at how we can verify that the two functions, the exponential and the log, are actually inverses of each other. At least we'll look at some evidence that we've looked at in the past. You might recall that in the past, if we graph two functions, something like y equals 1/2 times x minus 3, and we put in the line y equals x, and we'll make that a dashed line, you might recall that the inverse of this function, I think it's something like y equals, what would it be, maybe 2x plus 3. There we go. Looks good. If these two functions are inverses of each other, this one here and this one here, they should be reflections of one another about the line y equals x. Looks like they are. Well, let's take a look at logarithms. So what if I have something like y equals 2 to the power of x? Take a look at its graph, and by the way, let me zoom out a little bit here. There we go, so you can see kind of the details. And then let's take a look at y equals log, and I think I can put a base in there. I might have to do something fancy to make that happen. Let's try miscellaneous log. Where are you? There you go. Log base 2 of x, and what we can see is that this is the graph of the log, this is the graph of the exponential, this is y equals x. We can see that the two functions are inverses of each other by looking at their graph. Now, do we really care about that hugely? Not right at the moment, but I did want to at least show you, I wanted to prove to you that logs and exponentials are inverses of one another, and this is one form of evidence that that's true. So it turns out there's another way that we can take advantage of the inverse nature of logs and exponentials. And it relates back to this idea that that if we have b to the power of x and it equals b to the power of y, x must equal y. Well, when I talked about this property of equality for exponentials, I said it also works the other way around. So what if we didn't have this? What if we just had x equals y? The thing I was trying to say in the past was you could make both of these into the exponents of a base, and it would be legitimate. So I could take b and raise it to the power of the left-hand side, and take the same b and raise it to the power of the right-hand side, and this equation must be true if x equals y. We're going to try that over here. So what I'm saying is this. See how it's log base 3? I'm going to go ahead and take 3 and make a big 3. And I'm going to raise it to the power of log base 3 of x. And over here, I'm going to go ahead and raise this guy. I'm going to make that a base 3 and raise it to the power of 2. And by doing that, this 3 and this log 3, they cancel because of the inverse nature of logs. Again, remember what I was saying earlier. If you have square root of x, you can square it and get x. Just like if you have x squared and you square root it, you can get x. This is the opposite of what I showed earlier, where we took the log of an exponential. Now we're making a log into an exponent of a power, and therefore these guys cancel. So let's see what that looks like. It means that we get x equals 3 to the power of 2. In other words, this guy cancels with this guy. And so therefore x equals 9. Now, when we learn how to use our calculators with logs, we can verify whether this is true or not by putting a 9 in here and checking to see, does this really work out? Okay, so that is the inverse nature of logs and exponentials.